right? For example, for alpha hat you will be testing the following. Alpha hat will be alpha hat minus alpha upon the square root of sigma hat square summation xi square, yeah, and this will again be a t distribution with n minus k degrees of freedom, because the sigma hat square is that, right? Because sigma hat square is based on n minus k degrees of freedom. Here in this case n minus 2 degrees of freedom. So again you will compare with the t value. Again you will compare with the t values. That's how you take. Now there are some critical points that I want to discuss with you. How did we get this formula, for example? Why is this in the denominator? Or for beta hat, why is sigma square upon summation xi square in the denominator? You did the t test for beta hat, right? So you do beta hat minus beta upon the square root of sigma square upon summation xi minus x bar square. Why is sigma square upon summation xi minus x bar square in the denominator? Why? Because that is the relevant second row, second column of x dash x inverse. Right, because what is the variance of beta? Can I wipe this off? Now we are coming to a very important issue. So please remember that. We said expectation of yeah, right, which is you got this, right? So the variance of beta was given by sigma square into summation xi minus x bar square. So that formula is valid only to the extent that this formula is valid. Now, why is this formula valid? This formula, how did we get that formula? We said in general expectation E dash is omega, but we imposed two specific kinds of assumptions and then said omega is sigma square, and then got the sigma square out and you got this formula. So if those two assumptions are not correct, you can be in serious trouble. Right? You can be in serious trouble because what will happen is your OLS estimators will still have the property that expectation beta is equal to beta, because that property only requires expectation xi summation xi ei is to equal to 0. That will still hold. But what will happen is that the variance covariance matrix of beta hat, that is this is called the variance covariance matrix of beta hat. Now you know why it's called the variance covariance matrix of beta hat, because the diagonal elements are the variances, of diagonal elements are the covariances. The variance covariance matrix of beta hat will no longer be sigma square x dash x inverse. So if you take elements from sigma square x dash x inverse to calculate t values, you will not get the correct estimates of the variance of beta hat, variance of alpha hat, etc. And therefore your t values will go wrong. Your test of hypothesis will go wrong. There will very often in a regression model where you regress yi on say x and z, and if x and z are mutually correlated among each other, then you will not get correct t values for x and z individually. You will not get the correct t values for x and z individually. Is this clear? Yeah. With here, no? So sigma square summation xi, because sigma square is outside the matrix, so sigma square has to go, each element of the matrix is to be multiplied by sigma square, right? Summation xi square upon n summation xi minus x bar square. right? These will be the covariances of alpha and beta. This is the variance of beta. This will be the variance of beta. Sure, but that is valid only as long as this is valid, and this is in general not valid. Right? This in general is not valid. We made specific assumptions to make it valid. For example, think of a situation where we have no autocorrelation, but we have heteroscedasticity. In general, remember, in general we are going to have variance of beta hat is S x dash x inverse, right? Sorry, x dash x inverse, we are going to have x dash x inverse x, right? Omega no, let's write it down properly. Okay? Expectation of yeah, this is what is going to be x. What am I doing? What am I doing? Whole transpose, right? Sure, this is going to be x dash x inverse x dash e dash x. Yeah? This is going to be omega. Now, omega in general is going to be the following. Omega in general is going to be sigma 1 square, gamma 1, gamma 2, gamma 3, gamma 1, sigma 2 square, gamma 2, gamma 3, gamma 1, gamma 2, sigma 3 square, gamma 3, gamma 1, gamma 2, gamma 3. Yeah? This is going to be the general. So now, if I replace, somehow I can estimate this omega. The true variance covariance matrix is somehow if you can estimate this omega and replace that estimate here by omega hat, then I will be estimating the real standard errors without making these two assumptions. Such standard errors are called robust standard errors or robust standard errors because they are not based on those specific, the standard deviation of beta, the square root of sigma square upon summation x hat square, for example, is the standard error of beta hat. That is the standard deviation of beta hat. The estimated standard deviation, the estimated variance of beta hat was sigma hat square upon summation xi minus x bar square. If you take the square root of that, you get the estimated standard deviation of beta hat, which is called standard errors, right? Now, summation, the formula for the standard error of beta hat, which is square root of sigma hat square upon summation xi minus x bar square, is based on specific assumptions. Only if you make those assumptions will you get that formula, right? So that formula is not robust to the violation of those assumptions. So if these assumptions don't really hold in the real world, sigma hat square upon summation xi minus x bar square will not be the estimated variance of beta hat. So its square root will not be the estimated standard error. The correct variances will be given by this formula. So this formula results in what are called robust standard errors. This formula results in what are called robust standard errors, and this is sometimes called a sandwich estimator. Right? Why is it called a sandwich estimator? Because you can actually see that omega hat, the meat, is sandwiched between two slices of bread. Right? And this matrix, x dash x inverse x dash, is also a very important matrix, which we will see in the next class. We will see what it really means, how to derive robust standard errors with these problems and so on. How much more time do we have? 20 minutes. Are you all tired? Very? Sure. So we'll stop now.